Hello, everyone. We'll have a short lecture today because our time is a little bit shorter, thanks to some students that gave a nice talk on strictly interval graphs. And I would like to do two things in this lecture. One is I want to give some general remarks about some ideas that you might follow up on in algorithmic graph theory. And then I'll give the formal talk that will be an extension of of our last lecture, in which I talked about factoring Boolean functions. So let's first start and mention a few things that we have learned and some ideas for you if you want to go on for projects or further reading and so on. We talked on our last lecture about cographs, and we talked last week about chordal graphs. Now, you all remember that in order to recognize chordal graphs, we used a process called lexicographic breadth-first search. Let's look at the pad here. So lexicographic breadth-first search was this technique, a special kind of breadth-first search, where as you explore the graph, you favor those vertices that have seen earlier vertices. So let me just describe it in general. You start off with all your vertices being the same. You choose the first one, and its neighbors get priority. In regular breadth-first search, you would just put them on a queue. But here, you put them there, but you don't commit to the ordering in which you're going to search them. And the non-neighbors have lower priority. Then when you choose the second vertex, of those vertices that have priority, they get split into those that have a higher priority and a medium priority. And the non-neighbors of the first guy also get split into those that have, say, third class and fourth class. When you go to the third vertex, again, it partitions each of those equivalence classes into two parts, those that are more favored of them and those that are less favored of them. But when two vertices sort of get separated, one is in front of the other, they stay in that order. And until they are separated, they are in limbo as to who's going to be the preferred vertex. Now, that kind of preference was exactly what was needed to recognize chordal graphs in linear time. And the details can be found in my book or, I guess, the previous lecture. Now, lexicographic breadth-first search, although it was born to recognize chordal graphs 40 years ago, well, after 20 more years, it matured and it grew. And it was able to do other things. In particular, was used to give a recognition algorithm for unit interval graphs. Now, unit interval graphs, as we know, are those interval graphs that have representation where the intervals are of unit length and that they are equivalent to the proper interval graphs. And the use of lexicographic breadth-first search for a fast algorithm, there are quite a number of fast algorithms to recognize them, uses this idea of a two-sweep process. Two sweeps means that I do a lexicographic breadth-first search on the graph. It's going to be an interval graph, so it's chordal, and so the last vertex that I search will be a simplicial vertex in the whole graph. And then I throw away all that information and I only keep that vertex. And now I start a second sweep of breadth-first search using that as my start vertex and continue on. And then there's some conditions to check, and you can determine if it's unit interval. Now, look at this diagram that I've put it here. Well, what does this search do on the first sweep? It sort of says blindly I take a start vertex, like right here. Okay. And now I start searching, 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 and then eventually it'll end at one of the two sides, either at the left or the right. Or is it the left and the right? And so my simplicial vertex that I have found will be an extreme point on this representation. Now when I start the second sweep, I'm just going to be zipping across the whole representation, finding what I can find, and then check some conditions, and that's the way it goes. So this is very neat that we have Lex breadth first search working in a two-sweep fashion. Well, Derek Cornell didn't just stop there. He said, well, you know, this Lex breadth first search has to be good for other things too. And so while he and Michel Habib and Christophe Paul had another algorithm for recognizing cographs in a linear manner, well, they said, well, let's see if we can do something with lexicographic breadth first search. And guess what? They have a modified version of LexBFS where you do a first sweep, get yourself an order, keep that order in mind, and now do another sweep of the graph where you give priority according to the first ordering. You have to do the second sweep a little bit different. You're actually doing it sort of on the complement, and the details I would recommend that you read in their paper on the simple algorithm for recognizing these cographs. But the idea of having a two-sweep algorithm that uses modification of Lex breadth first search was a beautiful, kind of a beautiful thing for algorithmic graph theorists. If we had another lecture on cographs, I would show you that algorithm. But since we don't, at least not this year, I recommend that you go and do some reading on that or implement the algorithm. In general, I hope in this series of lectures, I've sort of whet your appetite to read more papers. And if there were to be a follow-on seminar or follow-on projects, take papers that are related to what I've talked about, more modern papers, and take an excursion looking at those new topics. I would call that Journeys into Algorithmic Graph Theory. And I think that on September 30th, 2018, I would actually like to release a new book called Journeys on Algorithmic Graph Theory. That will be these new kinds of topics that people might want to explore. Now, onto the factoring of logic functions using graph partitioning. So you'll remember that yesterday, as we talked about cographs, we said that was a special kind of Boolean function that we could recognize and factor quickly. And they had this special property that you could factor it into a form where every variable appeared exactly once. It's a very special kind of function. Now, I'd like to report on some work that where we used that as a kind of subroutine to work on the general property of factoring Boolean formulas. The idea is you have some formula, maybe you have it as a DNF, a sum of products, or some other form. You would like to have some algorithm that somehow factors it into a shorter, smaller expression, because that will be cheaper if you want to implement the gates in a certain kind of circuit. Now, that's a problem that people have been working on for 50 years or longer. I remember when I was your age learning about algorithms to do that. All of these problems are very hard, very NP hard, and so we use heuristics. And here we're going to be presenting yet another heuristic that seems to work very nicely and has some nice graph theoretic underpinnings. So I will tell you about this proposed method. I'll remind you read one's functions, but the idea will be we'll move on to something called the cluster intersection graph, some sort of separability function and partitioning a graph, and then in the end, our factoring algorithm, a heuristic algorithm called fx factor. And we'll analyze some of those parameters of how to maybe tune it. So here we have our introduction. Remember that factoring Boolean functions will be to derive a minimal factored form, that is, as squeezed as possible, from, let's say, an input of sum of products. Here's an example that is a read once function that we saw yesterday. If this is the original input, then it can be factored into something shorter. Now, the complexity in general of this problem is hard when these are general functions, which can also have negations. The read once we assumed would be a positive, but now we're going to jump into the swimming pool and have to swim through the whole sea of all sorts of Boolean formula. Now, there's two known algorithms, the algebraic methods, like Q factor and good factor, and there are Boolean methods. And these are what are known in the, I guess, in the disciplines of electrical engineering and the bowels of University of California at Berkeley. And all these algorithms work with some sort of technique called division. Our method is going to look at it with a completely new light. We're going to use graph partitioning, and we are going to exploit the locality of literals. We're going to identify read once functions and factor them separately, because we know how to do that from our last lecture. And we're going to try to, because they are fast to factor and frequently appear in the lower levels of logic. So, you know what a read once function is. It is a function where I can factor it so that every element appears exactly once. Here I put in negation, but you notice that C is always negative, B is always negative. And we recall that read once functions are a subset of unate functions. They frequently appear at low levels of logic design, which is a claim from the paper by Peer and Pinter, where they tested a whole library of functions and found lots of, that most of them seem to be of that form. And now let's move on to general functions. So I want to call a cluster to be a set of literals in a prime implicant of a sum of product representation, or you could work on the dual, a product of sum representation. Here I have a sum of product representation, and the clusters are simply the terms here. So I have cluster ABD, cluster ABG, and so on. And now I'm going to create something that you're all familiar with, an intersection graph. I'll call it the cluster intersection graph. The nodes correspond to the clusters, and two clusters will be adjacent if they have a common element in them. So here I have my clusters, and edge ij if cluster I intersects cluster G. But moreover, I'm going to give a weight to that edge to be the number of common literals between the two clusters. This is already familiar to you because you've seen it in chordal graphs too, right? Where we have, our clusters were cliques, and here our clusters are these terms of a formula. So here, for example, 4 clusters, ABG and CG have G in common, so it has a weight of 1. ABD and ABG have 2 in common, so I weight this 2. So this is my weighted cluster intersection graph. Now, theoretically, I'm going to talk about a separability function, which is going to somehow measure how easy it is to partition my graph into 2 pieces. And the separability will be high if it's hard to cut through without paying a high price. And the separability will be low if I can find a cut across edges that will be relatively cheap when I add up the weights on the edges that I cut. So choose a minimal separability and return its value. That is, partitioning the vertices into 2 sets A and B and counting up the weights on all the edges that go from one side to the other. Let me also just some notation. P to S means an algorithm like De Morgan's law or something like that that converts a sum of product form to a product of sum form. S to P means the same kind of thing, convert product of sum to sum of products. And P to S, S to P will be a shortcut, meaning that's just a shortcut term for take what you have and convert it to the other one. Okay. So here is the outline of this method. I have my function, and I represent it as a parse tree. All that means is, like any kind of expression, you can represent it as a tree. And our algorithm works on that input function, or its tree, and it checks, is this tree a read once function? Is my function a read once function? If it is, voila, I lucked out. I construct the read once tree, and I can exit. That is, if it's read once function, I have a stopping condition. If it's not a read once function, then I'm going to have to do something, and what I'm going to do is to split the graph into 2 parts and work on it recursively, but not exactly. Otherwise, I'm going to, first of all, construct the cluster intersection graph corresponding to T, which we showed, and I'm going to calculate its separability. Separability simply means how well can I partition the vertices into set A and set B so that the sum of the weights of the edges cutting between A and B is small. Well, there I'm also relying on some sort of heuristic algorithm that I get from a library on how to partition graphs. That alone is a hard problem. So I calculate the best I can do of how to separate it. And if the separability is not 0, well, that means that the graph is connected, because if it was 0, you'd have 2 separate components. Okay? Then, before you do anything else, build T asterisk, T star, by converting my formula from whatever product of sum to sum of product or the other, and construct the cluster intersection graph for that version and calculate its separability. Then I'm going to choose the best of the 2. That is, if the separability of G is lower, then I'm going to try to partition G. And if the separability of G star is better, then I'll go for the partition of G star. So here is an example. If this is my function, here I have my cluster intersection graph. The best way for me to cut it is this yellow line. It has a cut value of 2. Any other cut would be more than that. So this is the best I can cut if this is the graph. And that was the sum of products. Now, if I convert it to a product of sum, There I have this cluster graph. AC is a cluster, AG, BC, and DG. Here's its, and now I can cut with this yellow line with only a cost of 1, which is better than 2. So I choose this one. So what does that mean? It means I'll take the Boolean function represented by one side, which is AG and DG, that's on the left, and AC, BC on the right, and I'll call one of them F1 and one of them F2. Now I call my algorithm recursively to do the best I can on those. Then what happens when I return with that best solution? Well, I just take the best solution for F1 and F2, and I substitute them into the original. So I have AG, DG, that's the second and the third. So I'll substitute F1 for that. I'll take whatever I get as the best for F2, and my function then is F1 times F2. That's how the recursion works. Right? Now F1 was this, happens to be a read once function, and I could do it as well as possible. F2 also happens to be read once, so I did that fast. And now when I put them together, AD plus G, which is F1 times F2, I have a factorization, and this seems to be a really great heuristic. Now, if you ran it with the library routine good factor, it would produce this factoring, which is not very good. Okay? So it's good factor, but it's not very good on this example. Boolean factoring, which takes more time and is more complicated, and I'm not going to describe either of those, but it's a different library function. It would produce the same result as X factor, the best one, but it would take a lot more time than X factor. Here are some empirical results. Here are 1, 2, 3, 4, 5, 6 different functions that we took from some library of Boolean functions that were not that big. The number of literals, when we factored it, using 4 different algorithms: quick factor, good factor, Boolean factor, and our X factor. What happened? Well, for this function, we tied Boolean function. We got a little bit shorter. In this function, again, we tied and were much better than algebraic. In this one, we tied and improved. Here, for some reason, Boolean factoring was worse. We tied the others. And this, we tied, and everybody's pretty much the same. And here, again, we tied Boolean function. Here's another one where everybody is about the same. Here, Boolean factor couldn't even be run because it was too big. Notice how the literals, the number of, the length of the expression has grown. On the previous one, these were relatively small. On these big ones, Boolean factoring just collapses sometimes. Here it's about the same, and so on. Here we have a whole string of functions that came from some library where we ran everything. Good factor, we couldn't run Boolean on any of these, I think. We ran good factor. You can see good factor is the pink line, and X factor is never worse on this test set. If you just add up the total number of literals for all of that collection, then these two, this is like the sum of the lengths of all of those factored forms. You see that we're really a lot shorter. Okay, so this is the idea, and now we have some tuning to do to our algorithm. And let me tell you about that. Some of the parameters that you might have to play with to see what was good would be the cluster graph type. That is, do you make a distinction in this case between A and not A? Do you treat them as just A, occurring in one form or the other, or do you treat them as separate A and A bar? What does that mean? It means in terms of the cluster intersection, if you have, let's say, AB and A not C, do you join them or not? You join them if you consider A and A bar to be the same literal, and you do not if you consider it to be separate. Okay. That's something to play with. Another was to play with weight balancing. That is, when you partition, do you try to partition your A and B so that they're sort of the same size, or you don't care about that and you just try to partition them in any way? If they're kind of balanced, then in your recursive call, what happens? You're working on smaller problems that are about the same size. If the partition could be skewed, well, that might change the performance a little bit. So you have to play with that. The partition cut value, whether you use a certain refinement technique that graph partition algorithms are known for. You put that heuristic in or you don't. And a few other toggle switches. And you run that to see what seems to be best, and then you choose what seems to be best. Okay. And you also modify how you define your separability. Do you do it just on the basis of the weights across, or do you do some other kind of fancy thing like trying to take the size of the two sides and divide it by some other factor to see how to characterize and choose your separability, whether you just add them up or you weight it in some fashion. Okay, so we did some optimization on that score. It's not important what that optimization was. It's like in every engineering problem. You have to tune your parameters and you take what seems to be. And these were sort of our conclusions, that it always paid to use the literal type of cluster intersection graph. That is, make a distinction between A and A bar. Most of the time it was good to balance the edge weights. It was always good to use a modified cut size, and so on. Here were some combinations of different tests that we won't go into it. There's a kind of fundamental question: does better partitioning yield better factoring? That is, this partitioning is somewhere inside my algorithm as a sub-algorithm. Well, if you partition better, did that result in better factoring? Or maybe it didn't. That's something that needs to be checked on a particular library if you are interested in optimizing your library. So in all of these kinds of things, you give people options and then you let them try it out on what they are going to be working on. That's a kind of rule of thumb anytime you're doing a real-life application. If you are trying to do some kind of optimization and the graphs that you're working on are of a special kind, then use your algorithms that will favor that extra structure. Okay, so just in summary, we have presented this new method of factoring logic functions using graph partitioning. And it, of course, is optimal on read-once functions. And the empirical results show that it is better than the fast algorithms, and it is just as good but faster than the slow algorithms. Okay. So with that, I give you yet another way that we've used cographs here embedded as a subroutine at the low levels of the recursion for a heuristic algorithm for factoring general Boolean functions. Thank you very much for your attention.